Hello everyone. In this video, we're going to take a look at parallel circuits with the equations that go along with them. Uh, I hope you finished up your parallel circuit lab. I'll get that back to you as soon as possible so you can compare the equations you're about to see with the numbers you got using the tools in that simulation. So here's a look at a parallel circuit again. We've got three branch parallel circuit. Uh, the first equation we're going to take a look at is going to be Kirchhoff's junction rule put into mathematical terms. Remember, Kirchhoff's junction rule deals with current. And it says, okay, if your current's coming in to a junction, it's going to split. Some goes one way and some goes another. Well, if we take a look at a parallel circuit like we have on the screen, we've got three loops of current, a green one, a blue one, and this pink one. So as the current leaves the battery, hits the first junction, some of it goes down through our first resistor. The rest goes along the top wire. We would call the current going through this resistor number one, current number one. As this now pink and blue combo current comes into this junction, the blue part of the current goes down this way through what we would call resistor number two. So the current is called current number two. The rest goes through resistor three. We call that current number three. So the way the current splits up by the junction rule is going to give us an equation that says the individual branches of current, the blue, green, and pink, all added together will tell us our total current. So this is hopefully what you saw in your simulation. When you put the ammeters in a line that only had the resistor, you read one current, and then another current, and then a third current. And then when you put an ammeter in the line with the battery, you read sum total, which is the combination of those three individual currents. This is very different from our series circuit current equations where they were all equal. That's not the case anymore. In parallel, the currents individually running through each resistor all added together equal the total current drawn from the battery. And that's what the equation down at the bottom here says. All right, let's go to the Kirchhoff loop rule and take a look at voltage. Remember, Kirchhoff's loop rule says, okay, you're going to gain voltage in the battery, and then you lose it going through resistors. And any one loop the current goes through is going to gain voltage in the battery equal to the voltage it gains through the resistors in that loop. Well, in a parallel circuit, let's look at the green loop first. You're gaining voltage in the battery. Let's say it's a 9-volt battery. Well, you're going through only one resistor before you go back to the battery. All those 9 volts is going to pass through resistor number one. And you gain 9, lose 9, gain 9, lose 9 as the circuit flows. If you take a look at the blue loop going through R2, it's the same story. You gain 9 in the battery, you lose 9 going through 2. Same story again for number 3. All three of these light bulbs will contain the same amount of voltage as the battery. And that's exactly what our equation for voltage in parallel says. The total or equivalent voltage from the battery is equal to all the voltages going through the resistors. V1 over here, V2 measured right there, and V3 measured through bulb 3. So really, if you were paying attention and comparing these equations to your series equations, the V and I equations have switched between our series circuits and the parallel circuits. Now, resistance is the kind of a weird series of equations. When you're trying to take a look at the total resistance of a parallel circuit, you combine Ohm's law with these Kirchhoff rules, and the equation is very non-intuitive. Here's Ohm's law, R equals V over I, or V equals IR if you want. The only way that this law will work out mathematically is if the resistance in parallel is added in this strange-looking inversion fashion. If you want to solve for the total resistance in parallel, you'll need to take the individual resistance values of those resistors, add them together with their inverse. So that means 1 over the first resistance, plus 1 over the next one, plus 1 over the next one, et cetera, et cetera. And then all that added together is not going to even tell you your total resistance. It's going to tell you 1 over that total resistance. So what I like to do is modify the equation the way it's written on your tables and take a look at the very bottom equation here, where You're adding up 1 over this one plus 1 over that one, and then taking that answer and raising it to the -1 power. It's mathematically identical. Don't try and be fancy and say to yourself, oh, well, if I'm, 1 over this mathematical sum, why don't I just add them up, R1 plus R2 plus R3 like you did in the series? It doesn't work like that. That's not how math works. You can't distribute a exponent into pieces that are added. That only works with multiplication. If this math is, if I'm losing you with the math a little bit, I'll show you some examples. It's not as tough as it looks, and I'm not going to give you any problems that aren't, nice decimals, no irrational numbers. But I'm going to show you an example all the same. So here's our equation again. Let's say we have 3 resistors in a 3-branch parallel circuit like we saw in the picture, R1, R2, R3. We're going to add them 1 over each. Before we look at the numerical example, though, I'd like you to understand a little bit of concept with parallel circuits. Really, that's because parallel circuits are the circuits you use in your house. Your wall outlets, as you plug things in, they're all parallel circuits. You might remember from series circuits with the comparison, the series circuit's very inefficient. If one part of a series circuit goes out, the entire circuit goes out, and that's not very practical. So all the circuits you use in your life, for the most part, are parallel circuits. When you plug things in parallel, you make a new branch of circuit. What this does is it gives the electrons more options to flow around that circuit. They have 2 loops, 3 loops, 4 loops. Every circuit, every resistor or thing you plug in adds another pathway for each electron. This will decrease the overall resistance of the circuit. Sounds weird. I have a circuit with 1 resistor, I put another one in parallel, and your mind says, oh, I'm adding resistors. That should increase resistance. It doesn't. It decreases total resistance because you're giving the electrons more pathway. They overall have less resistance to their flow around the circuit if you give them 2 options rather than 1. You can try it out mathematically if you want, but I'm going to show you an example right now. And this is how you actually trip your circuit breaker. I read all of your circuit breaker investigations. Many of you had stories about using hair dryers and vacuum cleaners, or maybe toasters and microwaves at the same time. These appliances that draw a lot of current, since they're all in parallel, each one you plug in or turn on adds a parallel branch to a circuit, and that will decrease the total resistance, therefore increasing the total current coming from the power source. And that's what trips the breaker, too much current. You plugged in too many parallel pieces into a circuit. But let's get to the numerical examples already. You're going to notice here with our examples that the total resistance in a parallel circuit is always less than the smallest resistor in that combination. So let's try an example with 1, 2, and 3 ohms, all in parallel. So here's our equation again. 1 over the first one plus 1 over the second one plus 1 over the third one. Inverted is our total resistance. So we're doing 1 over 1 plus 1 over 2 plus 1 over 3, and then inverting that answer. So we're looking at 1 over 1, that's 1. 1 over 2, that's 0.5. 1 over 3, that's 0.333 repeating. We're adding all that together and raising it to -1. You punch that in a calculator. I mean, I've got the numbers on screen here for you, but our final answer comes to 0.5454 repeating. That is less than 1 ohm, which was our smallest resistor in that combination. Now, like I said before, I'm not going to give you a resistor combination that gives you strange decimals. It'll be nicer than this, but just for the sake of the example, I wanted to try a 1, 2, 3, and this is what we see. I want to give you one more example with numbers that are much different from each other. Let's try this again with another parallel setup of a 500, and 50,000 ohm resistor. So you imagine you say, oh, I've got a 5 ohm, a 500 ohm, and a 50,000 ohm. This is going to give me, the 50,000 ohm, that's a lot bigger than the other two. That's going to dominate the circuit. Let's just take a look at the math and how it works. Here's our equation again. 1 over 5 plus 1 over 500 plus 1 over 50,000. Well, I translated those fractions into decimals for you here, but we're adding those 3 numbers up and raising them to the -1 power. And we're getting an answer of 4.95 ohms. Now, The 5 ohms was our smallest resistor in that triplicate. And like I said before, the total resistance is always less than the smallest. So we knew going into this that the total resistance has to be less than the 5 ohms. What we're looking at here is an example of the 5 ohms really dominating the total resistance value. Just conceptually think about why. If I've got a 3-branch circuit, 5, 500, 50,000, the 50,000 ohms has so much resistance that barely any electrons are going to go through it. 500 ohms to a lesser extent, but most of the electrons in that circuit will go through the 5 ohm resistor. So it's not as if the 550,000 ohm resistors aren't receiving current, but they're receiving much less. So in the grand scheme of the circuit, most of the electrons are going to go through the path of least resistance, the 5 ohms. And that's why our mathematical total resistance value is so close to that 5 ohm resistor. This is just me trying to mix concept with the math. If I'm losing you a little bit with the concept, just stick with the math equations. Again, I'm going to make the numbers simple for you, but I'm trying to explain why this works the way it is. And one last tip I have for you with these resistance equations. I know it's not the easiest equation. You have to definitely use a calculator for this, but you can save yourself some trouble. If you want to add resistors in parallel, only 2 at a time, there is this alternative method to solve. Instead of doing this 1 over plus 1 over and then 1 over that entire answer by raising to the -1, if you're just doing 2 at a time, you can instead take the sum, that is, add the 2 resistors, also multiply them, get those 2 values. You take the sum, divide out the product. So let's say I've got resistors of 1 and 2. I would do 1 plus 2, take that, and divide by 1 times 2. So then that would be 3 over 2. The total resistance of a 1 and 2 ohm resistor is 3 over 2, or 1.5 ohms. 3 over 2, 1.5 ohms. So you can try that out if you'd like, or not. Just stick to this version of the equation. It's up to you how you'd rather solve. And I'm sorry, it just occurred to me that my example just now that I spoke out, 3 over 2 makes 1.5, yes, but that's solving for our 1 over total resistance. So in that case, it would be flipped again. The total resistance would be 2 over 3, or 0.66 repeating ohms. Sorry about that. I didn't realize that my picture here keeps the inversion on the left side as well. So this is missing the to the -1 power that I put up here. So sorry if that confused you. There are a few examples or rather a few more examples of using the equation in the next couple slides if you'd like to look through it yourself. But hopefully you don't have too much trouble with the exit ticket calculations. Please use a calculator. It's all fractions adding, -1 powers. But let me know if you have any questions. I do want us to understand these equations before we go any further with parallel circuits. Good luck, and I'll see you in the next video. It occurred to me that my example just now that I spoke out, 3 over 2 makes 1.5, yes, but that's solving for our 1 over total resistance. So in that case, it would be flipped again. The total resistance would be 2 over 3, or 0.66 repeating ohms. Sorry about that. I didn't realize that my picture here keeps the inversion on the left side as well. So this is missing the to the -1 power that I put up here. So sorry if that confused you. There are a few examples or rather a few more examples of using the equation in the next couple slides if you'd like to look through it yourself. But hopefully you don't have too much trouble with the exit ticket calculations. Please use a calculator. It's all fractions adding, -1 powers. But let me know if you have any questions. I do want us to understand these equations before we go any further with parallel circuits. Good luck, and I'll see you in the next video.